All right, boys and girls, welcome back to the drive-thru for a special rare live taping in Fifth Bell this year, 2017. Let's hear it for Fifth Bell. Yes, okay? And we'll see how this goes. Cylindrical, no big deal at all, okay? Let's go back one. So it's all cylindrical is polar with a Z. Okay, that's all it is. So just remember that in 3-space, we have to go back to the basics here. It's a right-handed system. That's X. That's Y. Down on the XY plane, we just change that into R. And then still, the reason I write that X on there is because you got to remember which axis we're rotating from in the positive. Okay? And so this is still our theta. And then the Z just points directly above that. Okay, and that's how far up or down we want to go. And so this point right here is R, comma, theta, comma, Z. Just like polars, it gets weird when R is negative. You know, so you just got to watch out for this. I will tell you we won't use this that much. Okay? It's most useful for cylinders. Okay? Also, kind of useful for cones. So here's an example of when you might use it. The only reason we have these other set of coordinate planes or axes is to make it easier on ourselves. That's the only reason. So that tells me that we will probably, when you guys are super smart, well, you already are super smart. If you ever get on past this and you're specifically probably in engineering, you might just come up with your own coordinate systems. Whatever's easiest for the thing that you're doing, you'll create coordinates that set that up. Then the calculus will be simple, okay, if that ever happens. I don't know if that'll happen or not. But that's definitely what's going on here. Someone just said this would be so much easier. Because if you look at this problem, you've got a Z equals this. And for the record, you're probably thinking, we could just do this in polars. I think I agree, which is why I don't think cylindrical matters that much at all. We're just going to set this thing up. So you got a Z equals this, so you got what's essentially a density function. Because we already have a 3, so this is a upside down cone, if you remember this, if you got out your oids. So if I could just graph this real quick, let me just take a pause. So what this thing looks like is just okay, so that is Z equals 1 minus the square root of x squared plus y squared, okay? Now, inside of there, you've got a varying density, and that's this equation. So to find the mass, you'd have to do a triple integral, right, with a function on the inside, and it'd get really nasty with x's and y's and z's. You would probably switch it to polars, but instead of polars, you could think about it as, I could tell you we're going to go, let's see, dz, dr, d theta for this. Okay, so let's see. What's theta doing? All I got to do is look at my picture. Remember, it's above the z-plane, so theta is going from 0 to 2 pi. Okay? What is my r doing? Conveniently, well, let's see. We can rewrite this as z equals r, right? It's the square root of r squared. R squared equals x squared plus y squared. Okay? And then this one here, this surface, is what? Z equals this one right here. 1 minus r. Okay? So, the plane is z equals 0. R, this point right here then becomes 0, 0, 1. And so r is just going from 0 to 1. You could also imagine that this right here at the bottom, let's see, this is a radius of 1. Okay? So then we just got to think, what's z doing? And very nicely, z starts at the plane z equals 0, and it goes to now just 1 minus r. Okay? Our height is r. But then we still have our Jacobian or our factor, and for this one I'll tell you it's still just r. Okay? Our factor is still just r. So that's what you do. It would just be the integral of r squared in these bounds, and the calculus is very doable. I'm actually not going to do it because it's in your book, and I can show you it in here. You end up getting pi over 6. You could do all the calculus by hand. You would need your calculator to do it in rectangulars. Okay? So that's it for cylindricals. Not a huge jump at all. Okay, Connor, great point, and I am wrong about this. This is wrong. Okay? This would be like, what's our notation for density? P. It's rho. This would be rho equals r, not z equals r, because rho is a function of x, y, and z. Now in this case, z is not a variable, but it could be, because we got to think three-dimensional triple integrals. Our density functions are now of 3 variables, no longer polar laminar, or no longer planar laminos, which were just 2 variables. Excellent, Con. You just saved this from being yet another terrible video. Maybe. We'll see how far it gets. All right, so look. Sphericals. Rho, phi, theta. That's how you read those things. Okay? So rho is no longer our variable for density. Now it's our variable for radius. So it might be easiest to see if you hit the lights. This is rho. It's the distance between the point that we have chosen and our old-fashioned origin. Okay? Phi is easy to explain. It's arbitrary, but phi is the angle between the z-axis and the segment formed between the point of our choice and the origin. Okay? So phi is the angle here. Now, theta is easy for you to understand because you're experienced with polars, but it's kind of hard to visualize. So for theta, you've got to do the old flashlight trick where you shine the light from above, okay, and project that thing onto the xy plane. Okay, so you're projecting the shadow of the segment onto the plane, and then theta is the normal positive rotation from the x-axis. It's essentially the same theta it was in cylindricals. Because the other way you can think about this is, don't think about it as starting with a segment. Think about it as coming out how far you want to come out, rotate to theta how far you want to rotate, and then rotate up, I guess, the complement of phi. That's kind of another way that you can think about this. And again, it always goes back to why. So don't ever stop asking that question. Why are we doing this? This would be to make integration of things that were spherical easier. There's enough things in our world that physicists care about. Atoms, planetary bodies, my figure, that are easier to calculate in spherical coordinates. So someone invented this. Okay? So, now, this is a hard picture. It's the same picture we just had. But now, they're trying to explain things, which has caused them to kind of trace over some of... So you just got to understand that all this is trig. Okay? So what they're saying is, a way to calculate z, Okay, look, you see this right triangle? So this is opposite. Well, it's not phi, it's the complement of phi. Okay? So one way to calculate z is just to take our radius and multiply by the cosine of phi. I think that should make sense. If I drew this triangle upside down and drew my right angle there, okay, according to phi, what is rho? Opposite, adjacent, or hypotenuse? Hypotenuse. And what is z, which is right there? It's adjacent. So cosine of phi is z over rho, right? Cosine phi is z over rho. So then what is z again? It's rho cosine phi. So I bring that one up to you because it's the one that's most easily understood. The other two are quite complex. So how far do we go in the x direction? Well, it's r times cosine theta, and that would have been simple. Okay? But we don't want it in terms of r, because r is simply how far we came out in the xy plane, and r is not a member of our spherical coordinate variables. So we don't want to reintroduce r, okay? So what they did was, instead of writing it as r, well, r is equal to rho times sine of phi, okay? If you go back to this upside down triangle, I think you could figure out maybe that this is r, right? So sine of phi is r over rho. Okay, so what's r again? Rho sine phi. Okay, cool. That's what that says right here. Okay? You're never going to have to come up with these for me. You will be given these things, but it's important to me that you understand where they come from. It's just trig. It just starts to look really, really complex. Got it? So, if I made you do three-dimensional Jacobians, which I didn't, we could now at this point figure out what our Jacobian was for rectangular to spherical. But I'll save you that, and I'll just tell you that it's not as simple. And let's see. Okay, so I'll give it to you. So, remember before you used to have an R down here, and that stood for region? Well, now it's volume. It's not exactly the same thing, okay? All right, here's your Jacobian. I'll change colors. It is rho squared sine phi. And again, we'll find out, and then they just give you the order as d rho, d phi, d theta to remind you that you've changed your bounds, okay? So I don't think I'm even going to ask you to remember the Jacobian multiplier. Like, I think I'll give that to you. This is all about just experiencing a new set of axes, planes, system, and then understanding how to do the calculus in it. All right, so here's our example. Okay? Bruce walked in first. Sometimes I think he might be an alien, so I chose Bruce. Okay? They've decided to steal the Earth's atmosphere. Okay, they're going to take it back. Have you guys ever seen Spaceballs? This is kind of like the plot of Spaceballs. Okay? They're going to use Mega Maid. She's gone from suck to blow. It's such a great movie. You guys should definitely see Spaceballs. Okay? All right. So, first of all, the note that the book gave me is that this isn't even close to being the density of air. So no snide remarks from you guys on that one. Now we got to try to set this problem up. We'll try to set it up. Let's see, I don't think we need the explanation. Do you understand what they're doing? I think what we need is right here. Okay. So, well, I think you can hit the lights now. So, this thing is going to be, first of all, let's pick rho squared sine phi. And I'm just going to tell you that we're going to do this d rho, d phi, d theta. Okay? So the first thing we got to do is pick our bounds on our theta. Anybody got an idea what our theta is going to do? 0 to 2 pi. Okay? Essentially what this is like a hollow shell of a sphere. You know? We don't want the mass of the Earth. We just want the air that starts at radius 6,400,000 and goes to the radius, well, I guess we'll do that. We'll do that last, okay? All right, so what about our phi? Okay, phi. I don't think so. If we go 0 to 2 pi, you're gonna. This is where polars gets weird. You're gonna start double tracing. We went all the way around our waist. Okay. Oh yeah. That's exactly right. Okay, I'm gonna explain what David's explaining to me. Phi is the angle between Z and our chosen segment. So all we needed to do is cover that much. Because we're swooping this thing around, I'm making a swooping motion with my arm for those of you guys following at home. Okay? Look, this is weird. It's cool. But I'm telling you, he's right and that's right. And maybe you'll understand it better when you practice. Where are we at? Okay? All right, so phi is 0 to pi, and as Dave stated, it's never more than that. It is sometimes less than that maybe, but who knows? Keep in mind, never done this assignment ever. You guys are the first people that have ever walked through Sycamore that have done it. So even if you fail, you're better than the last crew. Chocolate? Oh, that a boy. Strawberry is the better of the milkshakes. Go to Rally's. They have banana milkshakes. Unreal. They're like 99 cents, like everything else at Rally's. And then, if you really are feeling randy, ask them to make it half strawberry and half banana. It's amazing. But they might spit in it. Okay, finally. I'm probably not supposed to say that on my videos. What's our radius doing? What's our rho doing? It's going from 6,400,000, which is the air on the surface of the Earth, to 6,420,000. Now, I've screwed this up, okay, so I'll rewrite it in the next one. But what have we not taken into account at all? The density of the air, okay? So check this out. We said that's 10 to the 6th. Over 6 to... Okay, what's our H, though? Our H is our rho minus 6,400,000, right? So if we substitute that in, these are going to conveniently just cancel. And you end up getting that our density function, which I can't call rho anymore, so I'm just going to call it good old-fashioned capital D, ends up being 10 to the 6. It's like over rho. That's it. You guys get that? Okay? So now, when we put that in there, what's that going to do to our rho squared? It's going to cancel it, so we're going to end up with, and I'm going to stop writing the bounds on the integrals because it'll take too long, but I am going to go through and do this calculus. We end up with triple integral of 10 to the 6th rho sine phi d phi, no, d rho d phi d theta, okay? So, you get double integral. First of all, we're going to take our 10 to the 6th out, okay? And you get double integral of rho squared over 2 from, 64 to 642 of that, okay? So, the next line looks like this. 10 to the 6th times the double integral of 1.282 times 10 to the 11th sine phi. Now we're going to integrate that thing with respect to phi. So we're going to factor that back out. So now our exterior constant becomes 1.282 times 10 to the 17th. Okay? You get that? Just multiply it by 10 to the 6th times the integral from 0 to 2 pi of negative cosine phi as phi goes from 0 to pi. And now we're only left with theta. Okay? And so that's pretty easy. We're going to integrate. That ends up being 1 when you do that work. So you get 1.282 times 10 to the 17th times the integral from 0 to pi, of 2. Yes, it would be 2 to theta. Okay? Nope, just 2. Just 2. So, you end up getting 2 theta from 0 to pi times that, which is 1.611 times 10 to the 18th kilograms. Sorry, yeah, it's 0 to 2 pi d theta. Yep. Because then you end up getting 4 pi. Yep, like that. And then you get 4 pi. And 4 pi times this is what gets us to the extra 18. Okay? So if we had the right density function, we could have properly estimated the weight of our atmosphere. And that is atmospherical calculus. Boom! Boom!